In 5.1b, we're going to use simulation to model chance behavior. Let's formally define a simulation. It is the imitation of chance behavior based on a model that accurately reflects the situation. So if you're asked to model a situation and do a simulation, they're going to talk about a 4-step process that you can follow. The first step is going to state what's the question of interest about the chance process. Step 2, make your plan. Describe how you're going to use the chance device to imitate one repetition of the process. And then clearly define what the outcomes of the chance process are going to measure. Step 3, actually do the actual repetitions of the simulation. In step 4, make a conclusion about the simulation. We did a simulation with the 4 textbooks, and we actually did something of this nature. The key here about simulation, though, is to emphasize that the answer is just an approximation for that particular set of trials we particularly did. So let's talk about how might you do a simulation of this scenario. This is a hiring discrimination activity. An airline has just finished training 25 pilots, 15 male and 10 female, to become captains. Unfortunately, only 8 positions are available right now. Airline managers announced that they will use a lottery to determine which pilots will fill the available positions. The name of 25 pilots will be written on identical slips of paper, which will be placed in a hat, mixed thoroughly, and drawn out one at a time until all 8 captains have been identified. Okay, a day later, the managers announced the results of the lottery. Of the 8 captains chosen, 5 are female and 3 are male. Some of the male pilots who were selected suspect that the lottery was not carried out fairly. One of these pilots asked our statistics class for advice about whether to file a grievance with the pilots' union. Keeping in mind again, we had 15 males and 10 females. 5 females got the job and 3 males did. Is it time to file a grievance based on a gender issue? Let's simulate it. Let's use state, plan, do, and conclude to actually set this up and carry it out. Okay, so the first thing we want to do is determine how likely it is that a fair lottery will result in 5 female and 3 male pilots being selected from the pool of 15 male and 10 female. Kind of already talked about that. Well, what's our plan to do that? Well, let's make a special deck of cards. In that, what we could do is we have to simulate the 15 men and the 10 females. So what they're suggesting here, to make the 15 men, why don't we use a combination of hearts and diamonds? So we will use all 13 heart cards and then 2 of the diamonds. So we have 15 red cards. And then let's use 10 of the black cards. How about the spades to represent the actual women? So again, the red card here are the males and the black cards are the females. All right, fine. We have what it looks like for the people. So let's shuffle and deal out 8 cards. Count the number of, we're curious about the female cards. All right, and that's what we're going to record. If we were to do this as a class, we would maybe ask each student in the class to do it 5 times. If we have 20 students, that'd give us 100 trials. That's a nice long run number. It's a nice length of the simulation. Fine. That would be 100 trials. So then in 100 repetitions, we could actually make our conclusion. So let's go ahead and do the simulation. Assume that we've had all of those trials taken place. Here's what the results looked like. All right, so we ran the simulation and we counted how many females, and here's our dot plot. Well, how would you conclude this? Remember, they are having an issue that it was 5 or more female pilots. If you look at this dot plot, how many times did 5 or more female pilots happen? Well, in this case, you're going to actually count 9 dots because this was only 50 trials. So I'm going to double that and say it was 18. And 18 out of 100 times. So let's make our conclusion. In 100 repetitions, 18 yielded 5 or more female pilots. Because if 5 was unlikely, 6 was unlikely, 7 was unlikely. So count those 2, a more extreme case even. So that is going to be about 18% of the time. In a fair lottery, would we choose at least 5 female pilots to become captains? So from this, we conclude that the company could have carried out a fair lottery. As their statistician, would you advise the men to go against the union and bring up an issue? In this case, I would not, because it is somewhat likely to happen. The AP Board does give you good advice here. When making conclusions, students will lose credit for suggesting that a claim is definitely true. In this statistics class, we're running simulations, and here's what this simulation said. Maybe a different one would have been slightly different. So don't be so defined by saying exactly or definitely. It's better to say, like they are saying here, there is or isn't sufficient evidence to support the claim. And we will talk about this more when we hit Chapter 9 and do hypothesis testing, where we have to be very specific on how we make our conclusions. Now let's actually walk through 2 simulations for these notes. And we'll do them in the formal state, plan, do, and conclude 4-step process. First scenario. Suppose I want to choose a random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper, mix them up in a large grocery bag. Just as I'm about to select the first name, a thoughtful student suggests that I should stratify by class. I agree, and we decide that it would be appropriate to select 4 seniors and 2 juniors in this case to get my 6. However, since I've already mixed up the bag, I don't want to separate them again. Instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means, however, that I may need to select more than 6 names. Because if I get, 8 seniors in a row and I have to keep drawing until I get a junior, it's more than 6. So design and carry out a simulation using Table D to estimate the probability that you must draw 8 or more names to get 4 seniors and 2 juniors. Okay, let's talk about what we're going to state. What is the deal we're dealing with? Here it is. What is the probability that it takes 8 or more selections to get 4 seniors and 2 juniors? Okay, what's our plan? Well, we're going to use Table D, so let's think about it this way. Everyone is already numbered, and we know that we did, the seniors were from 01 to 60. Therefore, our juniors were going to be from 61 to 90. So let's state this. Using pairs of digits from Table D, we will label the seniors 01 to 60 and the 30 juniors from 61 to 90. The numbers 00 and then 91 and 99 will be skipped, so we have to keep that in mind. We're going to first move left to right. Let's pick a row, across a row. We look at pairs of digits until we have 4 different labels from 01 to 60 and 2 different labels from 61 to 90. We will then count how many different labels from 01 to 90 we actually had to look at until we got our 4 and 2 combination. That's our plan. Let's do the actual simulation now. Here's an example of one repetition using line 101 from Table D. So here's line 101. And if we look at that, remember 01 to 60 is a senior. So 19 would be a senior. The next is 22, that's a second senior. Careful for the next one, we actually have to do 39, that would be a third senior. Then we get 50, we have our 4th senior. Now, we get to 34. Well, that is a 5th senior, so we just skip them. 5 would be the 6th senior, skip it. 75, we finally have hit a junior. And then the next one is 62, which categorizes a junior, so I can stop. It took us in this one exactly 8 selections. So if we were to run a simulation on this, and let's say we would have everyone do 2 simulations and it would make a class plot, hoping to get 50 trials. If we record our results here, so we could do our 8 right now, what will it look like? Running this simulation 50 times is going to result in this particular dot plot. So based on this, the question is, what's the probability it takes 8 or more times to do this? Well, if you look at our dot plot, and this was out of 50, this right here shows up that we have 12 here, then 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. we actually have 25 out of 50 meet this requirement of 8 or more extreme than 8. So let's now make a conclusion. We can say in this simulation, 25 of our 50 trials required 8 or more selections to get 4 seniors and 2 juniors. So the probability that it takes 8 or more selections is approximately 50%. And remember, simulation means approximately, not theoretical or exact. Let's look at one more, picking teams. At a department picnic, we have 18 students in the math and statistics department, and they decide to play a softball game. 12 of the 18 students are math and 6 are statistics. To divide into 2 teams of 9, one of the professors put all the players' names in a hat and drew out 9 players to form one team, with the remaining 9 forming the other. The players were surprised when one team was made up of entirely math majors. Is it possible that the names weren't adequately mixed in the hat? Or could this have been happened by chance alone? Let's design and carry out a simulation. Again, state, plan, do, and conclude. Let's state the scenario of what we want to analyze. What we want to analyze here, what is the probability when randomly assigning 12 math majors and 6 stats majors to 2 teams that there will be one team with all math majors? That's the question. Now, think about how we can actually set this up. To simulate this, we have 18 people. Remember, 12 math, 6 stats. So why don't we do equal size pieces of paper, do 12 of them with M's and 6 of them with S's. If we do that, 12 with M to represent math, 6 to represent stats. We're going to shuffle the papers and just put them in 2 piles, one of 9 and the other 9. Divide them into 2 piles of 9. Count the number of math majors on each team and record the number of math majors on the team with the most math majors. We're trying to see if we ever get a team with 9. So let's run the simulation. I'm actually going to use the calculator for this one, and I'm going to do random integers just to show you this. I'm going to pick from the numbers 1 to 18, and I want them to put all 18 in a random order. Keep in mind, I'd have to say no repeats if repeats show up. So ignoring repeats. Let's go ahead and pick the first 9 people on the team. So team 1, remember 1 to 12 is math. So if we take a look at this, team 1, we have our first 9 players, 15, 18, 9, 8, 5, 12. Don't repeat 12. Don't repeat 15. 14. Don't repeat 9. 17, don't repeat 12, and 7. If you count these up, that includes and gives us 5 people on the math, therefore there's 4 stats. And I really don't even have to count for team 2, by the way. I can just do the math for it. I know that if there's 5 math, there has to be 7 math here, 6 stats here, there has to be 2. Now, what is the most amount of math people we have on any team? It's going to be right here of 7. So for this case, I would record a 7. I want to run this enough times, so let's repeat this entire thing 30 trials and see what we get for our outcome. This right here is our dot plot of the 30 trials. So let's figure out how to make our conclusion. Since only blank trials in 50 resulted in a team with all math majors, well, in this case, there's only one. So one trial resulted in all math majors. The probability is only going to be 1 out of 50 would be a 2%. Since getting a team of all math majors is unlikely, we could conclude there is sufficient evidence that the names were probably not shuffled very well in the hat. Notice the use of the word could. We're not saying we definitely will or we exactly will. We're kind of being a little wishy-washy in this, and that is totally fine.